Let's take a look at our next one. Right. Let's say h of x is 1 over x squared plus 1, right? And we need to start taking some derivatives. So we'll actually write this as x squared plus 1 to the minus 1, okay? We'll do some u substitution. So we'll set u equal to x squared plus 1, and then u prime is equal to 2x. So then h prime of x, first I take the derivative of this guy where this is u. So that's going to be negative 1 over the thing that I called u, which is x squared plus 1 squared. And then I need to multiply by the derivative of the inside, which is 2x, and that's our derivative. For our second derivative, we're going to need to take the quotient rule. So we'll do low d high. The derivative of negative 2x is just negative 2, minus high d low. And to take the derivative of this, we're going to do a sort of similar argument. 2 times x squared plus 1, right, treating this guy as u, times my derivative of the inside, which is 2x. Okay? All over x squared plus 1, well, low squared, so to the fourth. And then if we simplify here, I see a factor of x squared plus 1. That should be a plus. I see a factor of x squared plus 1 in both of these. So I can factor that out. That should be squared. And then what are we left with? Well, we're left with minus 2 times x squared plus 1 plus what? Well, this factor is gone, so we get negative 2 squared times a negative 1 times 2 times 2x. Looks like 8x squared, right? Over x squared plus 1 to the fourth. And then when you simplify this inside, right, and cancel one of these, you're left with 2 times 3x squared minus 1 over x squared plus 1 cubed. Took a little bit of work, but this is our function. And then from here, right, now that we've calculated the second derivative, we can start to use it. Okay, so what I'll do is I'll take this information to the next page and then clean it up a bit. Okay, so that way we can use it to actually analyze our function, and we'll get rid of all of this. There's probably a more efficient way to erase all of this, but I haven't found it. So we'll just kind of scribble. And then here we have our derivatives. So what do we know? Well, in order to use the second derivative, we need to look for the places where it's equal to 0 or it does not exist, right? This is always going to exist, right? Because we don't consider the complex numbers ever in this class. And so our function always exists. And so that means it's going to equal 0 whenever this top equals 0, right? So that means it's 0 when 3x squared minus 1 equals 0, right? So that means it's, equals 0. And if you do some manipulation, add the 1, divide by 3. So, when x squared equals 1/3, or x is positive negative 1 over the cube root of 3. And there's no need to rationalize this in this class. For the most part, we don't need to rationalize any of these answers. We're totally fine with the square roots in the denominator. Okay. And okay, now that we have this, right, we should look at how the sign changes. Well, we'll put 0 there. We'll put 1 over the cube root of 3. And we'll put negative 1 over the cube root of 3. Sorry, the square root of 3 for both of those. And let's start to think about this, right? Well, at 0, what's going on? Our denominator is always positive. And then at 0, this is 0, minus 1. So we have negative 2 on the top over 1. This whole interval is negative, right? Because our function is 0 there. So that means between it, since we're continuous, we're always a singular sign. And then what about over here, right? 1 over the cube root of 3 is going to be less than 1, right? So let's just pick 1. Here we have 3 minus 1, which is going to be, 2. This top is positive. The denominator is always positive. So we're positive here. Likewise, actually, when we pick negative 1, this is also going to be 3 because the square is going to get rid of it. The denominator is always positive. And we're positive here as well, right? Now we need to check that our function is actually defined at these points, right? So let's just take a look at h of, say, 1 over the cube root of 3. It's going to be 1 over a third. I keep saying cube root. It definitely says square root. 1 over 3 plus 1, right? 1 over 3 plus 1 is going to be 1 over 4/3, or 3/4. And actually, 1 over the negative square root of 3 is going to come out to the same thing, right? Because that squared is going to get rid of the negative here, okay? So then 1 over the square root of 3, comma 3/4, negative 1 over the square root of 3, comma 3/4 are our inflection points. And then for our last example of this little run, I've cooking showed it up for you because it was a little bit dense in terms of the writing. And this is sort of, teasing a little bit what we're talking about in the next section, which is curve sketching. But here's the situation, right? We have some information about our graph, and we want to sketch it, right? And, notice if I were to actually give you, the polynomial function that has these ideas, we could take that polynomial, solve this information, take some derivatives, get all this. We could totally do that. And then, once we've collected it, we could graph it. But we're just going to graph it from this information because maybe it's not a polynomial. Maybe we just know this behavior, okay? And let's sort of put these pieces of information down one at a time. So we know that at negative 1, we're at 1, 2, 3, 4, right? So I guess we'll, make it clear that we're going every other, right? At 0, we're at 2. and at 1, we're at 0. Okay, what else do we know? We know that our tangent lines at -1 and 1 are horizontal. Right, so I'll just sort of draw little tangent lines here. Further, right, notice that around -1, right, here on this side, we're positive. Here on this side, we're negative. And since we're going from a positive slope to a negative slope, we're going to have a local maximum right there, right, where I guess I'll, sort of color code where all of this information comes from. Okay. Well, we can sort of turn our attention down here, right? We have a flat tangent line, and we're negative on this side as seen here, and positive on this side. So that means we have a local minimum right there. Okay, well, what else do we know? But as we draw our attention to here, let's sort of look at something. Well, on the negative interval, we're concave down. On the positive interval, we're concave up, right? So that means that we have a point of inflection here, right? Further, back from this green area, we know that we're decreasing here and increasing here, right? So with that information, right, we can reason through sort of filling in the rest of our information. We're going to be increasing here, right? And we're going to be increasing here. And we also know we're going to be decreasing here on that interval, and we know we have a point of inflection right there. And indeed, we can check visually that we are concave down here and concave up there. Okay. One thing even further that I want you to notice, okay, is that right here, we're concave down the whole way, and we have a critical point. And I want you to think about whether or not that forces our critical point to be a local maximum, okay? And indeed, it actually does, right? When we're concave down and we have a critical point, we need to have a relative maximum. Likewise, when we're concave up, right, like what's going on here, here, and we have a critical point, well, then we automatically have a relative minimum, right? And this is actually such a useful thing that we, write this down as something called the second derivative test. And as per usual, I've cooking showed up the second derivative test for you, okay? And I'll sort of walk you through it, right? First, we're going to compute f prime and f double prime, right? In order to, use the second derivative test, we need the first and second derivatives. And then we find our critical points of the first derivative, right? Just like we did for the first derivative test. And then we actually feed these points not into the first derivative and analyze the behavior around that point, but into the second derivative. And if our second derivative is negative, notice that means we're concave down. And when we're concave down, oh, look at that, it's a relative maximum, right? Similarly, if we feed our point into the second derivative and it's positive, well, if it's positive, then we're concave up. And if we're concave up, we have a relative minimum, okay? Unfortunately, one of the downsides of the second derivative test is actually this third case. If we plug in our critical point, into our second derivative and we get 0, then our test is inconclusive, right? It's not that it's, a maximum or a minimum or neither. The test just fails. And then we need to go back and use the first derivative test in order to actually get ourselves an answer, okay? So we can do a very quick example of this using our longtime friend from the last little bit, x cubed minus 3x squared minus 24x plus 32. Our first derivative, I'm actually going to factor it. We did this last week. So you can, just recall this. And then we computed our second derivative earlier today, 6 times x minus 1, right? Well, here's what I want you to notice. Our zeros here are critical points, right? What are our critical points? I guess I'll just write that out. Our critical points are x equals -2 and x equals 4. Well, we can use the second derivative test for these, right? And calculate f double prime of, say, -2 is 6 times -2 minus 1, which is -18, right? Which is less than 0. And since it's less than 0, x equals -2 needs to be a relative max, right? Simply because our second derivative is negative, right? We can also take a look at the second derivative at 4, right? It looks like it's going to be 4 minus 1. 4 minus 1 is 3, times 6 is positive 18, which is greater than 0, which means x equals 4 corresponds to a relative minimum. Okay, that's how easy the second derivative test is. And so you might just wonder, well, why don't we use the second derivative test all the time? Why even bother with the first derivative test? And, well, it's because of our third case, right? The places where it's inconsistent, right? That's, sort of makes it not the most reliable. Well, it's not even that it's unreliable. It's just sometimes that it doesn't work, right? And, when it doesn't work, we can always fall back on the first derivative test, right? The first derivative test will always give us a conclusion, but the second derivative test is a little bit simpler to run, okay? You only need to plug in one point. You do need to take an extra derivative, right? They're the kind of thing where it works well in different cases, okay? But ultimately, our first and second derivatives work together to help us characterize our graphs, right? There's sort of four cases that we can worry about, that we can kind of throw in a table, right? We can have our first derivative is positive and our second derivative is positive. We can have our first derivative is positive and our second derivative is negative. And then I'm sure you can guess where these are going. Negative and positive. And then the final case, right? First derivative is negative. Second derivative is negative. And what's again nice is the way these work together will characterize our graph, right? In the red case, we're increasing and we're concave up. So the rate that we're increasing is increasing. In the green case, we're increasing, but we're concave down, right? So we're increasing, but the rate that we're increasing is decreasing. For yellow, it looks like we're decreasing, but we're concave up, right? So maybe something like that. And then in the purple, we're decreasing and we're concave down, okay? So these sort of four pieces of information here, that actually makes, this process a little bit easier, right? We could look at the interplay between, here, what we've called green and orangish yellow. I still don't know quite what color that is, to sort of get these little arcs here, okay? And that's sort of why, or rather one of the reasons, right, for why we care about these higher order derivatives, right? They, among other things, right, allow us to analyze these functions in a new way because of, this interplay here.